welcome back to the Algebra 2 series. Today we're looking at variation and Newton's law of universal gravitation. This is a variation, and it's described in that blue text there, and we use the word force. So for our variation, question part A, write the relationship as a variation equation. We will use the force here as our solved variable. So I'm going to use capital F as my force, and then we'll make an equation from there. So it states here that we have two objects. It varies jointly, so that means I'm going to have a couple of variables there. And I also have an and and inversely. So it looks like this is going to create for me a fraction. So I'm going to write a fraction bar first. And let's take a look at that numerator. It looks like our two objects vary jointly. So that's just m1 and m2, the two masses. And I put my coefficient of variation in the front of that. Now the coefficient of variation will change in representation, but it won't change in value depending on the application, whether it's something in space or something in our physical part. But it's the same value all the time. It is a coefficient to be used there. And then finally it states, and inversely with the square of the distance between them. So that distance squared is going to go in our denominator, and it'll look something like this. So we have a relationship as a variation equation. That takes care of the first part. Now let's see if we can use this a little bit to figure out some concepts with gravitation. So the first question comes up: how does the force change when two objects are moved from 12 feet apart to 8 feet apart? So what we're doing here, it looks like we're taking it from 12 to 8, so we're only changing our denominator, and the question is, how does that affect the force? I'll write this down as two different force values then. The first one will be force number 1, and that will be K times M1, M2, and that's going to be 12 squared, or 144. That's pretty easy. Force number 2, it's going to be K times M1, M2, and that's over 8 squared, or 64. Well, one of the things we learned in the past is that these fractions, when they change like this, it looks like our denominator on the right is smaller than the denominator on the left, but the numerators are left unchanged. So we learned that for non-negative denominators, the smaller the denominator, the larger the overall fraction. So our first thing to notice is that the force has changed. It has gotten larger because of that smaller denominator. So we're looking for a comparison of this force to this force, and the first thing we notice is that it got larger. So obviously some partial credit would be given if you just said it got larger. But we want to know how much it got larger. So one of the things we want to do is try to figure out how it got larger, and in this case it's going to be by some factor. And I like to write it this way. I ask myself, what could I multiply that first force by to generate the second force? And in this case, if I multiplied it by a very simple value, 144 over 64, then the 144s would cancel, and I would generate the second one. So that kind of helps us to recognize what the resulting factor was. So I'm going to write this down. Let's see, that means that the factor change was 144 over 64, and I can simplify that a bit. They both divide by 16 evenly, so that would be 9. If I can do that in my head there, and 64 divided by 16 is 4. Oh, I did that fast. Okay, 9/4 is the factored value. So we would then say that the force increased, so we want to include that, by a factor. So this says it didn't just increase like 9/4 units, it increased by a factor of 9/4. That's an important statement because it involves several things. It increased, it was a multiplicative value, a factor of 9/4. And finally, the last thing to note is that this thing was from 12 to 8. It didn't even decrease by half. So it went from 12 to 8. That 8 isn't even half of, it's less than, excuse me, it's greater than half of 12. But look at how much the force increased. 2.25. 9/4 is 2.25. So the force increased significantly, even though the distance only went down from 12 to 8. So that's kind of the take-home message there. Let's finish this video out with the last question, which is, if the masses of the two objects are doubled and their distance is also doubled, then what will be the change in the gravitational force? In this typical problem, we would write down that the force is equal to K times m1, m2 over d squared. And now we're going to create a new force from this. So we're asking, what is the new force? So maybe just call this F2. If I double each mass, so that would be K, it would be 2m1 and 2m2. And here's the key to this little problem is I'm doubling the distance, so that's going to be 2d quantity squared. And notice now we've got father-grandfather, as we have in the past seen in class. That 2 right up there is going to distribute to the 2 and the d. So working this down, we end up with the 2's here. Again, those are all multiplied together, so we can combine them and bring them to the front. That would be 4k m1 m2, and the denominator would be 4d squared, because that is a distributed power because we have multiplication right there. As they cancel, we end up with k times m1 m2 over d squared, which is no change in the force. So we would write F2, and then if we wanted this is equal to, that is equal to the same as we started. So no change would be the answer. Very interesting problem. You know, that third part C, you almost suspect that there will be a significant change somewhere, but in this case there is none. Well, I hope you enjoyed that very brief example of Newton's law, and there will be other similar type problems as we go through this section.